Hello and welcome to this webinar. Today's topic is air hygiene indoors. We will have a look at some basic facts and then talk about measuring methods and technology. During the current pandemic, we have noticed an increasing demand for tools that enable experts to assess indoor air quality. Usually, you find Pallas when you look for an aerosol technology specialist, and we have been active in that field for almost 4 decades. We offer leading technology to environmental protection agencies, to customers from industry, as well as to scientists. Today, we present one of our latest products, the AQ Guard, which is short for Air Quality Guard. I'm going to introduce this analyzer to you and explain its practical use for assessing indoor air hygiene. Up to now, indoor spaces are not monitored in general, since there is no regulation for air quality in place, apart from occupational safety in workplaces. If at all, the same limits for particulate matter as in ambient air have been applied. At Pallas, we always felt that more should be done, and based on our experience in environmental protection, we developed an analyzer specifically for indoor use. That development began sometime before the COVID-19 health crisis, but as it turned out, the product is very useful in the current situation. The COVID-19 pandemic is obviously driven by airborne transmission. A person suffering from an infection of the respiratory system emits droplets of various size, which contain infectious material. That happens, as everybody knows, during coughing or sneezing, but also, and that's often forgotten, when talking. And in fact, it also happens when we just breathe. And that's a fact that was previously largely unknown. Droplets settle and can contaminate surfaces, so we use disinfectants and wash our hands frequently. They can impact on others, which can be avoided by wearing masks, even simple ones, and we keep a safe distance to others. However, some droplets, in particular those emitted from deep inside the lung, are very small and don't settle. They remain airborne. That's what is now widely known as aerosol. So we have those small droplets coming from the lung, but even the larger ones also start to shrink as soon as they are exhaled, because the water, which makes up most of the droplet's mass, evaporates quickly. What remains is the core or nucleus, which can be infectious and which keeps floating in the air. An infection requires that small droplets are exhaled, that contained infectious germs survive some time, and that the concentration increases due to ongoing emission of more aerosol. And this is exactly what happens. We know from measurements of our own that COVID-19 sufferers exhale an increased amount of droplets smaller than 0.5 micrometer in size. Virologists have confirmed that the virus stays infectious for hours, and breathing constantly produces more aerosol, which is eventually inhaled by others. So what kind of measures should be taken, and how can we control that these measures are indeed effective? This will be discussed in a moment. There are, of course, many motivations to make sure we have healthy, non-infectious air indoors. Any organization strives to maintain high productivity. If illness leads to staff being absent or being able only to work less, the organization as a whole will be impaired. If you are unlucky and staff contract an illness which is under public health regulation, a part of your organization may be put out of action as employees are quarantined. No more production in that department, and possibly in others who depend on them. Apart from factual safety, In some situations, perceived safety can be just as important. For example, when people decide where they prefer to spend time, they will probably feel more at ease in a place where a display shows that measures are being taken to improve air quality and that those measures are supervised continuously. Your operating license or the number of persons permitted to enter your premises may depend on what measures for controlling air quality are in place and how they are being monitored. The air hygiene problem can, of course, be addressed in different ways. I'd like to explain in short why personal protective equipment like masks need to be backed up by additional measures. This slide visualizes how particles of different size interact with the filter material. Obviously, particles larger than the mesh size of a filter can't pass. These are the big blue ones. Smaller particles, the yellow ones, can pass, but if they impact on an obstacle, they will stick. They are still too heavy to travel around obstacles, so with multiple filter layers, we can catch them. The very tiny ones in purple don't travel on a straight path. They are kicked around by air molecules, and their zigzag path makes it more likely that they hit an obstacle. Unfortunately, virus particles have an intermediate size. The size of a virus or an aerosol nucleus is in the range 100 to 300 nanometers, where removing particles from gas is most difficult. They can pass through the mesh. They are light enough to float around an obstacle, but heavy enough not to be affected by collision with air molecules. They can thus penetrate a mask to some extent. Many people also don't know or ignore that masks must be adjusted to fit the face as tightly as possible. Masks worn at the workplace are often individually tailored, but the common masks available at the shops or pharmacies are often put on carelessly, allowing a large amount of air to bypass the filter material. And even a face piece that sits perfectly tight will lose efficiency over time and as it gets moisturized by exhaled breath. In summary, masks are important, but even high-quality masks worn properly can't be regarded as a fully sufficient safety precaution. We asked ourselves, of course, what we as experts in aerosol technology can contribute. Measuring particles is certainly most important, but there are some other factors as well. I'll come to that in a moment, but let's first take a closer look at the aerosol particles again. If you want to analyze the size spectrum of particles present in air, you need a so-called aerosol spectrometer, a device which tells you how many particles of which size are there. This is the result of such an analysis, showing the particle size distribution up to 20 micrometer. The number concentration of particles per size class is plotted over diameter. Please observe that both axes are logarithmically scaled. One horizontal line equals a factor of 10. Large particles make up only a tiny fraction of the total number. Small ones, on the other hand, can be present by the tens and hundreds. Viruses and tiny exhaled droplets are all below half a micrometer in size. Analyzing the bottom end of the particle size spectrum requires highly sensitive, scientific-grade instruments like a Pallas scattered light spectrometer. Our analyzers can detect particles even smaller than 0.2 micrometers. Simple, low-cost dust sensors, on the other hand, use a measuring principle that gets less sensitive below half a micrometer, and particles smaller than 0.3 micrometer are typically invisible to them. Such sensors are now widely offered. They are also typically integrated into mobile air purifiers, but they miss the decisive part of the particle size range when we look at airborne infections. Assessment of health hazards caused by aerosol nuclei is quite pointless if your instrument can't detect them. In this typical example, you find about 1,000 times as many particles at 200 nanometers compared to half a micrometer. A basic dust sensor may tell you that the air is perfectly clean, while in fact hundreds of particles the size of a virus are present per cubic centimeter. Now, as I said before, number and size of particles are important, but there are some additional parameters. Temperature, and in particular relative humidity of the air, have some influence. High humidity lets germs survive longer, while low humidity makes the tissue in our respiratory system more susceptible to attackers. A humidity between 40 and 60% is recommended. However, the most important factor is the number of particles per unit volume of air. This parameter determines how long it takes until breathing results in the uptake of a critical doses. We have to keep in mind here that lots of fine particles are present in indoor air, but most of them originate from other sources, not from people. Particles exhaled by people hide in this pollution background and can't be detected directly. How do we solve this? We can assume that aerosols exhaled by persons mix with the air in a room like gases do and use carbon dioxide as a tracer. Carbon dioxide is exhaled as well, and so the concentration of carbon dioxide indicates to which extent the air in the room is contaminated because some of it has already passed through somebody else's lungs. The local carbon dioxide level is correlated with the local concentration of possibly infectious exhaled particles. So now we have discussed the parameters which an analyzer should measure in order to assess the risk of airborne infection. Let's have a look at the device we have designed to meet these requirements. The AQGuard started out as an indoor fine dust monitor, derived from the technology we use in our FIDAS 200 dust monitors for environmental monitoring. As in the FIDAS 200, the AQGuard's particle detection system is equipped with a polychromatic LED light source and a highly sensitive photomultiplier tube as a receiver. It uses the light scattering technique developed by Pallas for sizing and counting single particles, and an adapted version of the FIDAS algorithm we use for regulatory monitoring in ambient air to calculate PM values. So first of all, the AQGuard is a top-of-the-line aerosol spectrometer, which covers the size range between 175 nanometers and 20 micrometers, and of course also a particle counter. So far, it's quite similar to other Pallas products. However, additional built-in sensors give an added value, and that added value goes beyond just displaying more data from more sensors. By combining the information, we can now offer benefits which go beyond just the sum of the information from the components. The most innovative feature is the calculation of an infection risk based on scientific models and the data measured. We can use this, for example, for continuous monitoring of a room to inform persons in the room about the level of risk for airborne infection. But we can also use the analyzer as a scientific instrument in a test scenario for assessing an indoor space from the perspective of air hygiene. As you can see in the feature overview, the basic version of the AQGuard is a monitor for the regulated PM values PM10 and PM2.5. Its functionality can be expanded by different add-on packages. Aerosol specialists or researchers typically want to add the Fine Dust Professional package to get detailed information about the particles. Those who are interested in continuous monitoring the air quality indoors choose the Healthy Rooms package. Now, what are the advantages of combining carbon dioxide measurement and scientific-grade particle sizing? First of all, a carbon dioxide sensor does not tell you whether air purification is active or not. If the air in the room is circulating through an efficient filter, harmful particles may be greatly reduced, while the sensor still indicates high risk. On the other hand, if you only take carbon dioxide as a measure and ventilate the room as frequently as the device tells you, you may end up with high heating costs in the winter. The particle number concentration, in particular the concentration of small particles, tells you whether air purification, that is, active removal of potentially harmful particles, is working or not. With appropriate equipment, experts can assess indoor spaces under controlled conditions and produce results which allow a comparison of different rooms, different usage scenarios, or different ways of using technical equipment to reduce the infection risk. A small graph showing schematically possible relations between particle number and carbon dioxide level can help to understand the concept. If the carbon dioxide level is low, that is near ambient air level, it doesn't matter if the particle concentration changes. That's most likely not related to persons in the room, or there is a high air exchange rate. If the carbon dioxide level rises, the risk may be higher. Persons are probably present, and among the particles in the air, there may be more which have been emitted by persons. High levels of carbon dioxide and particles indicate high risk. The room is populated and measures should be taken to exchange or purify the air. The AQGuard combines available data from different sources to display a risk indicator based on the present situation. There are more advanced options available as well. I'll come to that in a moment. Let us first have a quick look at the AQGuard again to see how to access data. The AQGuard features a compact PC and a small touch monitor built in, running Windows 10 Professional. All data is saved to the internal storage. With that, you have more or less all the options that are available on a typical PC. There is an Ethernet port, which can also be used for powering the device if it is connected to a power over Ethernet switch. The AQGuard runs on 12 volts and needs 15 watts of power on average. Wi-Fi is also available. By default, we have a hotspot running to which you can connect, but it's of course also possible to use it for connecting the analyzer to a local network. And there is a built-in cellular modem, which you can equip with a SIM card of your own. Information can be viewed on screen, viewed by remote desktop connection, or viewed by using remote control software such as TeamViewer. Data can be transmitted in real time over a network connection. Saved data can be copied to a USB storage or downloaded to a device which is connected to the AQGuard's built-in web server. That's how the interface looks on a device connected to the web server. The web interface is mainly for viewing data, and it adapts automatically to the screen space available on the client device. Interaction requires either direct access to the AQGuard or remote control, and I'll show you some examples now. These are some of the different dashboards available in the AQGuard's graphical user interface. At the start, the infection risk index and the air quality index are displayed. We can choose from a set of pre-designed dashboards There are diagrams, but also numeric views. On this dashboard, we see the air quality index to the left and the underlying data to the right. We can look into the data to find out why the air quality index displays a value equivalent only to average air quality. By clicking on one of the data tiles, we call a graph showing the associated data over time. Carbon dioxide is not to blame. We are just between 50 and 60 ppm above ambient level. So we go back and have a look at the concentration of aerosol particles next. The display shows that we have 66 particles per cubic centimeter, which is not a high value either. It also hasn't changed much over time previously, as we can see here. However, the level of volatile organic compounds is elevated. Currently, it shows 0.6 milligrams per cubic meter. It has been constantly high over the past 10 minutes. And if we look further back in time, we see that it has been rising over the last hour. Even 1 hour before, the level was already above 0.4. The limit level for good air quality is 0.3 milligrams per cubic meter. So that explains why only a medium air quality index value is displayed. The component that gives you the lowest quality determines the air quality index level, and here VOCs are to blame. Now, instead of only using the AQGuard for monitoring the air, we can also use it for risk assessment. We have seen that the carbon dioxide data gives us information about the breathing activity of people. Importantly, the carbon dioxide remains when people leave a room, so measuring carbon dioxide is even better than just counting the persons. We can use scientific models to associate carbon dioxide and infection risk with certain assumptions regarding the rate at which an infected person emits infectious material, the probability to actually have an infected person in the room, and how long susceptible persons would be exposed to the situation. What is new now is that we can track the particle concentration over time. If we observe a decline, it tells us that particles are either filtered out or diluted by admission of clean air. This beneficial effect can be combined with the traditional risk assessment models based only on carbon dioxide, which will result in a lower effective risk. And that is indeed what mitigation measures aim at, and with the AQGuard, we have a tool to measure it. So what do we propose for assessing rooms with the AQGuard? From our point of view, there are 3 scenarios. The first one would be to measure in a room that is being utilized as normal using only the AQGuard. You will need people in the room in order to have a typical carbon dioxide production rate. The main problem here is that you will experience interference. In particular, it may be difficult to deal with air exchange. Air coming in will also carry particles at an unknown level, and it's usually not possible to take that properly into account. The solution to that is using an aerosol generator, which produces a non-hazardous test aerosol. You can load the air with these test particles to a level far above the usual level in the room and also far above the level of ambient air or air coming in through a ventilation system. By doing that, you can consider outside air to be a particle-free dilutant. The dilution effect of air exchange can thus be examined. Secondly, you can now also more clearly evaluate the effect of additional mitigation measures, like air purification. You can observe the course of the particle concentration in the room over time with and without additional equipment being active, and so assess that equipment's effect. The infection risk assessment should be the result of a test under well-controlled and reproducible conditions. The carbon dioxide production rate is essential because this is the basis for the risk calculation. You will thus need a typical number of persons, wearing masks of course. If it's not feasible or not permitted to populate the room, you can instead release carbon dioxide in a controlled way. A release rate of 25 liters per hour simulates the presence of one person doing office work. Accordingly, 250 liters per hour or 500 grams per hour would simulate the presence of 10 people. And that's not really a large quantity. Even a small 3-kilogram cylinder can simulate 10 people over 6 hours or 60 people over 1 hour. I have already mentioned aerosol generation several times. The newly developed PAG 1000 aerosol generator is the ideal companion for the AQ Guard. It's a standalone device equipped with a speed variable pump and runs for several hours on battery. It has a sturdy stainless steel case and can easily be carried around. When operated with DEHS, which is a non-hazardous carbohydrate, it generates a long-time stable aerosol. The particle size distribution of the aerosol droplets has its peak at around 180 nanometers, so it simulates viruses very well, and the particles are ideal for measuring with a scattered light aerosol spectrometer. Its output rate is high enough even for large rooms. In order to make it as easy as possible for indoor air quality experts to assess a room, we have designed a software package for generating infection risk reports. The report is based on data from tests which run over a predefined period. This new indoor air hygiene professional package combines all the features of Finder's Professional and Healthy Rooms and adds the automatic report generation feature. Using an aerosol generator is, from my point of view, essential for indoor air hygiene professional, but is also a highly recommendable accessory for aerosol researchers. In this example, you see how we prepared a room for the test by increasing the particle concentration with the aerosol generator. Once we had achieved the desired level, we stopped aerosol generation and started the assessment. We set the recording period, 15 minutes in this case. Such a short period is okay if you work under perfectly controlled conditions. It would also be sufficient if you expect to see a quick decline because you employ high-performance filter equipment. Of course, it is also possible to run the test over a much longer period. Once the measurement has begun, it can run in the background, which means you could return to the standard dashboard to have a live view of the recorded data. The recording will run for the preset period. It can be stopped manually as well if you access this screen again. The assessment report will always be generated based on the data recorded between start and stop, whether automatic or manual. In this example, air exchange led to a decline of the particle concentration as well as to a decline of the carbon dioxide level. The falling particle count indicates that particles are removed. In general, this occurs by deposition on surfaces, or by dilution, or by filtration, or by a combination of these effects. Carbon dioxide level and particle count are taken into account for calculating the accumulated risk. The curves for the reproductive number in red show the result based only on carbon dioxide, that's the dashed line, and based on carbon dioxide and particle concentration combined, that is the solid line. The solid line indicates lower risk because the decline of the particle number concentration has been taken into account. In this case, the improvement is moderate. With an air purifier, we would have observed a more pronounced decline of the particle concentration and accordingly a lower infection risk. In this example, the accumulated risk over 15 minutes is equivalent to a chance of less than 10% that another person will be infected. However, these are model calculations based on qualified assumptions. The idea is not to calculate a true infection risk. We calculate a figure that can be used for comparing rooms and situations under standardized boundary conditions. Rooms vary considerably regarding geometry, furnishing, the number of persons present, available ventilation, usage time, and so on. Assessment is thus a task for experts. Our recommendation is to take a practical approach and carry out real-world tests with suitable equipment. Experts are needed to provide guidance in various situations. You need clear information about the initial situation in order to determine if measures need to be taken and for developing a concept. Once such measures are put to effect, such as changes to the ventilation system or installation of air purifiers, their effectiveness needs to be demonstrated. And lastly, periodic checks are recommendable to ensure ongoing effectiveness. The AQ Guard and the PAG 1000 are an ideal match and allow you to employ scientific grade equipment which is yet simple to use. They are valuable tools for experts in the field and can help them to generate new business. That concludes today's webinar. I hope you found it interesting and I thank you for your attention. If you have questions, please contact us or one of our regional sales partners. I will leave this screen on for some more time so that you have the opportunity to write down my email address. And I wish you today goodbye and please stay safe. Thank you once again for your attention.